So I'm probably best known in this sort of psychedelic research world as the person who put forward a mathematical critique of Terence McKenna's Timewave Theory, which I haven't got time to explain now. If you don't know about it, a lot of people in here will know about this. It was a sort of quasi-mathematical theory attempting to explain something to do with the nature of time. And it predicted a sort of singularity at the end of last year, winter solstice 2012. So there was a certain amount of interest in that through the 90s, and particularly towards the end of last year, I was being asked about this a lot, and then obviously since nothing particularly significant seems to have happened, and we're all still here, there's a lot less interest in that now. Unfortunately, this is not what I'm going to talk about. I've talked about that enough already. But it's something Terence McKenna got me thinking about. So I'll quickly tell the story of how this happened. It was 1994, and I was either just finishing or had just finished a PhD in pure mathematics. And I was a sort of young and somewhat naive Terence McKenna fan. I was really into what he was. I was reading his books and listening to his talks. And I was fascinated to know what he'd done, how he'd come up with this theory. There was no real explanation for how he calculated it. So I got in touch with him by email, which was quite a novel thing at that time, and I was amazed when I heard back from him. I got in touch and said, I'm a mathematician, and I'd be interested to know more about your theory, but also offered to give him a hand if he had any sort of other mathematically oriented ideas that he would like exploring. And he got back to me. I was amazed. He replied, and he said, yes, I've got this idea about prime numbers I'd like you to look at. And he didn't say anything about, he didn't provide me with the background to this theory until much later. And in fact, we had this rather sporadic communication for a few weeks or months after that. So he told me he had this idea about prime numbers, and he didn't actually say what it was. So I replied and said, great, I'd be fascinated to find out more. What's this idea? But I didn't hear back for weeks after that. So I had weeks to think about what would Terence McKenna be thinking about prime numbers. So I had to sort of put my psychedelic head on and try and imagine what prime number theory would look like through the sort of psychedelicized lenses of Terence McKenna's mind. And when eventually he did get back to me and tell me what the idea was, I was a bit disappointed. It was quite flimsy. It was sort of clutching at straws, really. He was hoping to be able to calculate big prime numbers with his time-wave theory, just merely in order to prove to the world that he was onto something. And it was pretty evident from the way it was constructed that wasn't going to happen. But in the meantime, I'd gone on this sort of mental mathematical journey, trying to look at prime numbers from a sort of imagined psychedelic perspective. And what I found quite fascinating, I had to educate myself in this area of mathematics, which I hadn't actually learned about during my PhD, and added in a few original thoughts of my own, and I'm going to attempt to share with you what I found, and which has strangely led me back to the idea of time again, which was the thing McKenna was most concerned with, and I'd like to think he'd be amused by this. So we'll start off with definitions. Now you probably all learned in school prime numbers are ones which you can't divide by anything except themselves or one, but that's a sort of boring definition you have to remember and think about. There's an easier way visually. So 15 is not a prime number because you can divide 15 beings into 5 piles of 3 or 3 piles of 5. 16 is not a prime number because you can divide it into 4 piles of 4, 2 piles of 8, 8 piles of 2. Similarly, 14 is not because it could be 2 piles of 7. But 17, there's nothing you can do with 17. There's no way you can divide 17 into equal piles of anything. You can't divide beings. Piles of 1 don't count because you can do that with any number. Basically, it doesn't matter what name you give 17, what symbol you represent it with, what culture you're from, which planet you're from, where in the universe, where you are in history, 17 beings cannot be subdivided. It's just like that. 18 can, 19 can't, 20 can, 21 can, 22 can, 23 can't, and so on. And it seems there's a sort of irregular pattern emerging here if we start to look at this very basic information which is just thrown at us by the universe as soon as we start counting. So I've plotted the first 10 prime numbers up there. So we've got 2, 3, 5, 7, 11, 13, so on. And then the first 50, first 100. And you start to see they're crowding together. They're sort of crowding together near 0, and then they're sort of thinning out slowly, perhaps. They're clustering in places, and there are gaps in other places. But the main feature of what you're looking at is irregularity. There's no obvious pattern there. In fact, it's the lack of pattern, it's patternlessness. It's what happens when you strip out all of the regularity of anything repeating, and you're left with the holes. But this is, as I said, fundamental information built into the structure of reality. So it immediately intrigued me when I started looking at this. Well, why, the thing with which we order the world, cognitively, counting, number, measurement, has at its root this, irregularity. The last place you'd expect to find irregularity. Now, if you add any more than 150 prime numbers to the number line, you can't really see what's going on anymore. They crowd out. So there's a better way of representing it visually, where you just build a staircase like this, where every time you find a prime number along the number line, you go up a step. So you can see where they are. Wherever there's a jump, that's a prime number down on the number line. You can also see how many have appeared because it's going up, so it's accumulating vertically and showing you how many prime numbers there have been found. And you can also see the gaps between them as these horizontal bars. So you can see the irregularity in how the gaps vary. And it looks like this thing starts off fairly steep and then it sort of levels off a bit. And it seems to be following a kind of curve. And in fact, if you zoom out, so we're looking at up to 100, now the top one we're looking out to 1,000, and yes, it's still made of this irregular staircase. We can imagine it being made of little square Lego blocks or something like that. But when we've got 1,000 blocks wide, it's very evidently following a kind of curve, at least approximately. When we zoom out to 10,000, that thick black line isn't particularly helpful. It should just be it'd be almost invisible at that scale. But we wouldn't see any blocks, we would just see a curve. So we have something going on here. We have an average behaviour going on with what's called the distribution of prime numbers. They thin out according to a very simple mathematical formula involving a logarithm, which I won't trouble you with. And that was something which was observed in the late 1700s and then finally proved in the late 1800s. So that's cleared up that level of what's going on with the prime numbers, but it still leaves this mystery of the irregularity. They're not exactly following the curve, they're approximately following it. So mathematicians are going to dig deeper and they're going to look at how are the prime numbers deviating from this approximate behaviour. So they're going to look at the difference between what the prime numbers are doing and what they're supposedly doing on average. And this generates something that can be represented like this. Again, don't worry too much about what it means. It's basically showing you, this is on the range from up to the first, or up to 1,000, prime numbers up to 1,000. It's showing you the extent to which the prime numbers are clustering together or thinning out with gaps more than they ought to be based on this average curve they're following. So where the thing goes up high above the axis, that's where they're clustering. When it goes below, that's where the density is lower, they're thinning out. So this object here then suddenly becomes the object of interest. This is the information given to us by the number system. Again, this isn't anyone's opinion or theory, this is just built into the nature of reality. This is what the number system does. And yet it looks like the kind of data that you might get maybe if you were looking at a radio telescope, picking up signals from outer space, or maybe stock market fluctuations, or animal populations, or electrical activity in the nervous system. It looks like something physical. And as a result of that, one idea is perhaps you could decompose it. You could attempt to analyse it with what's called Fourier analysis, which is a common tool in the physical sciences, where you take a signal like this and you attempt to break it down into these basic elements, sine waves. You're probably familiar with these. On the left are different examples of the basic units of vibration, whether this is in music or sound, in electronics, in quantum theory. You have these basic units called sine waves. They have a frequency, which is how squashed together they are that way. So we have very high frequency at the bottom, lower frequencies further up, and amplitude, which is how tall the waves are, which is sort of the volume, how loud the signal would be. So we have high and low amplitude. And you can add these things together. Mathematically, it's no problem to add these waves together. So you see the sort of running total on the right. What happens when you start adding them together? You start to get these more irregular signals. And as a result of that, it's possible to work the other way. If you're given an irregular signal, mathematicians or mathematical physicists would think to decompose that, to try and break it down into its waves, to work out what are the periodic elements that make up this signal. So what happens if we try and apply that kind of thinking to this signal here, which is just the signal that's coming at us out of the number system. We try and break it down and see if it's got a sort of harmonic structure to it. Now, there really is no reason why it should. So it was a huge mathematical surprise in 1859 when a German mathematician called Riemann showed, and he didn't do it visually, he did it with equations that look pretty horrendous if you don't understand what they mean. But he basically showed you can break down that signal we were just looking at into not the waves at the top, not sine waves, but these ones below, which are basically another version of the same thing, put through a kind of logarithmic distortion. But I like these waves at the bottom because they bear the same relation to a spiral as the ones at the top do to a circle. So I call these things spiral waves. It's just a shorthand for what would be called logarithmically rescaled sinusoids by mathematicians. So basically, if you add together an infinite set or an infinite sequence of these spiral waves of very particular frequencies, you get that irregular signal at the basis of the number system. And what do the frequencies look like? Well, these are basically, here they are, these are the first few. There's an infinite sequence, and you can calculate them. We've calculated billions of them by now. And they're known as the Riemann zeros, for a reason I won't try and explain. And unlike the prime numbers, they're not nice whole numbers, they're these irrational numbers, with these never-ending decimal expansions. Rather than thinning out, they cluster together. But what we're looking at here are basically the notes which make up this chord. It's like you're adding together infinitely many tones to make this infinite chord, which creates the number system. So I asked the illustrator that I work with on a series of books about this to create this character, this infinite-fingered jazz goddess playing a chord, bringing the number system into reality. I think he did quite well there. So I get infinite keyboard, infinitely many notes, but they have to be the right notes. And as I said, there's no reason why this prime number deviation signal graph thing I showed you should break down into a nice clean set of tones, but it does. And so it suggests a kind of music underlying the number system. And there's been some popularizations of this question to do with these frequencies. This is my contribution to the field as illustrated by Matt Tweed. You might remember Matt from the Space Gates back in the 90s. And back to the story, so these are the spiral waves. And by combining an infinite number of these with the correct frequencies, you get back to this, which allows you to reconstruct that, which shows you where the prime numbers are. So the mystery of the prime numbers has now been displaced. It's been solved effectively. We understand why the prime numbers look like that, why they make that irregular pattern, because they're an overlay of this infinite sequence of spiral waves of particular frequencies. But then the question becomes, why those frequencies? Where did they come from? And that's even more mysterious than the prime numbers. And this set of frequencies is also the subject of something called the Riemann hypothesis, which goes back to 1859. It's an unsolved problem. It's considered the number one unsolved problem. There's a $1 million prize for it. And even if there weren't, it's the problem that mathematicians would give their right arms to solve. Because all the roads lead to the Riemann hypothesis. Every branch of mathematics seems to be becoming more and more intricately linked to this problem, which underlies the structure of the number system, basically, the distribution of prime numbers. Now, here's where it gets really weird, because there are these things called dynamical systems, which have been shown to be strangely relevant to this question, which is the last thing you'd expect when you know a bit about mathematics and physics. So I'll give an example of dynamical systems. So a pendulum, a gyroscope, the weather, currents in the ocean, the particles orbiting the nucleus of an atom, or a group of atoms in a magnetic field, billiards colliding on a billiard table, planets orbiting a sun. All of these things are things which happen. There's an element of time involved. They evolve with time. They have components which move, and which at any given time can be located somewhere in space. And so mathematical theory has evolved to attempt to model these types of things, called dynamical systems theory. And it involves developing equations and systems of equations which will model or mirror these types of systems. So the idea being, you want to know what one of these systems is going to be doing at some point in the future. You insert the necessary time into the equation, and it gives you the relative positions in space of all of the components. So dynamical systems theory is obviously of great interest to people working in all of the sciences, and as a result, it's taken on a life of its own. It's become a branch of mathematics in its own right. So it's possible to study dynamical systems as things unto themselves, to classify different groups of them and study their properties, and to develop dynamical systems which don't actually correspond to anything in physical reality, which are just mathematical models of things which sort of happen in some kind of fictional way, and which you can discuss and have a consensus about, and as I said, study the properties of. So dynamical systems theory has evolved and has been, and this is just really very strange and really has not been explained yet, and I think points in very interesting directions philosophically in terms of our understanding of number and time. Because 4 different strands of research have all applied dynamical systems theory to this question of the distribution of prime numbers and these mysterious frequencies underlying them. So we've got Berry and Keating in Bristol, who've combined elements of quantum mechanics and chaos theory, and hypothesized a mysterious dynamical system which has a quantum mechanical associate with what's called an energy spectrum, which perfectly mirrors these Riemann frequencies. It suggests there's a sort of quantum oscillator of sorts underlying the number system, which is a very weird possibility, but they have very good reason to believe it mathematically. In France, we have Alain Cohen at the Institute of Higher Studies in Paris, who's working with these very exotic algebras, C-star algebras, type 3 factors. These are algebras which have a sort of internal dynamical structure. They appear to sort of evolve, even though they don't exist within physical space. He's drawn on areas of physics like quantum statistical mechanics with ideas like phase transitions and symmetry breaking. This is stuff that physicists talk about. He's applying it to the number system itself, and he's attempting to show that the Riemann frequencies are what are called an absorption spectrum of a type of quantum system. None of these people have been 100% successful in really solving the mystery of these frequencies, but everyone's been contributing. And these are all interrelated but different approaches involving dynamical systems. And so you've got Christopher Denninger in Germany, who's looking at what are called flows, a type of dynamical systems called flows, on things called foliated spaces. You can't make those in physical reality, they're just purely mathematical things, but the idea of a flow on them is a physically inspired idea. And Michel Lapidus in California, even more exotic spaces, non-commutative flows of on what are called moduli spaces of fractal membranes. Absolutely no way you could build one of those in physical reality, although the idea is inspired by physics. So we've mysteriously got ideas from physics shedding light on the number system, which is at the root of mathematics, which is at the root of all sciences. So there's a strange inversion going on, which I think tells us something about the nature of how psyche and matter interrelate. So that's another question. Quickly, what I meant by flow, this would be a flow in physical space of oceanic currents represented with lots of little arrows. This would be an evolving vector field. You would solve a set of equations to work out what that was going to do next. You can imagine sort of pausing and unpausing that and watching it evolve. An attempt to mathematically capture that in equations would be a dynamical flow. But any kind of dynamical model, these are 2 simple examples. One's just a cannonball or projectile being fired into the air and following a parabolic arc. The other one's a pendulum. In both cases you have a set of equations that you needn't worry about, but notice both sets of equations have a t in them. Along with your x's and y's and everything else, there's a t. T is time. So you put in a number for t, you want to know where that cannonball is going to be after 1.3 seconds. You put it 1.3 for t, and it tells you. Similarly, you want to know where the pendulum is going to be. You solve the equations, you put in your value for t, and it gives you a value for that angle, theta, which shows you where the pendulum is. So any kind of dynamical model has to involve t, a time variable. So if we've got a dynamical system underlying the number system, that brings up a very strange question, which is, what kind of time are we talking about? What's evolving here? Nobody's suggesting the number system is changing from day to day or moment to moment. It's timeless, it's not evolving. But yet something is evolving within it, or has evolved to it, or something. So we're forced to use these problematic words to try and capture what we're talking about here. Fictional time, virtual time, imaginary time, mythological time. I don't know what to call it, but all of this seems to be pointing to the fact that there's some kind of time-like dimension underlying what I call numerical reality or mathematical reality, the mathematical landscape. Whereas before it was believed to be a timeless thing, it looks like it now has something like a time dimension, but that's not the time dimension we're in. But what would that be? I don't know. Now, that's pretty head-spinning stuff, so I'm just going to use my last few minutes to take you through something that anyone can understand. You don't need to be versed in quantum physics or anything else. Just addition, multiplication, counting, just thinking clearly. So everyone can follow this. If you've been sort of phasing out a bit, you can pay attention now. This will also show you why prime numbers are related to the mystery of time. So addition and multiplication, we tend to think of them as similar things we learn about at school when we're young. They're buttons on your calculator with similar symbols. But they're very different, and both of them combine two numbers to make a new number, don't they? And you can do them in either order. So in some ways they're very similar, but in other ways they're radically different things. And to show this, we act them out physically. So to act out addition physically, 12 plus 7, starting at 0, walk 12 steps, then walk 7 steps, you've walked to 19. So you're basically, it's just counting, it's just extending counting. You count 12 steps, then you count another 7, you see where you are. You count 9 stones in a pile, then you count another 12, and you've got 21. So addition is pretty straightforward, it doesn't matter what order you do it in. Multiplication though, something different happens here, because the 12 and the 7, notice here the 12 and the 7 are both numbers of steps, they're both the number of steps you've taken. If you want to act out 7 times 12 instead of 7 plus 12, you have to take 12 steps 7 times. You have to take 12 steps to 12, and then another 12 to 24, another 12 to 36, and another. And you've done 7 lots of 12 steps. So 12 is the number of steps, and 7 is the number of times you do that. So 7 is acting on the 12. There's not the same symmetry. You can reverse them, 12 times 7, 7 times 12. But in either case, one's a number of steps and one's a number of times. And we talk about 7 times 12 as much as we say 7 multiplied by 12. We talk about times tables. We know intrinsically somehow that multiplication is linked to the notion of time. So now if we act out 3 times 7, there are various ways we can do this. We can count out a row of 7 beans. We can count out 3 rows of 7 beans. We can make 3 piles of 7 beans. We can count 3 steps. We can walk 7 steps 3 times. We can make 7 marks 3 times. In each case, there are 3 chunks of time containing a similar act. So the first chunk contains the making of a row of beans or a pile of beans or walking 7 steps or making 7 marks. And the other 2 chunks similarly contain a representation of that act. So if we're going to break time up, if we go in reverse, if we confirm that we have in fact counted out 3 piles of 7, we have to actually acknowledge, we have to clock each of the piles of beans. At some moment in time, we have to recognise that pile, that pile, that pile, to have counted 3. Okay, admittedly with small numbers, you can say, oh, there's a triangle or a square, so that's 3 or that's 4. But if you get into anything higher than that, once you get up to 11 or 19 piles, you have to actually count them. And to count them, you have to acknowledge each one in a separate moment. And then if you're counting piles of 7, to be sure that each one is a pile of 7, you have to, for each pile, make sure it's got 7 beans in it. So you have to individually clock each bean. So that means there have to be 7 moments in time where you acknowledge a bean. So if we then really analyse what's going on with this, and this requires paying attention, it's quite convoluted, but this really shows where addition, multiplication, prime numbers and time all come together. So she's counting out 5 piles of 9. So to analyse what's going on there, he's filming it. Then we step outside time into an editing suite and look at time as a piece of film. We cut the piece of film into 5 strips. The 5 strips all contain the same thing. They contain the act of laying out a pile of 9 beans. Now if it was just the act of making a sandwich, that would be done. We have 5 strips of film each showing the act of making a sandwich, but we have 5 strips of film showing the act of making a pile of beans. We have to check that the piles are the same. So we have to count in each strip of film that each one contained that the 9 beans have been counted into the piles. So to make sure that we've done that right, we have to film ourselves counting on the film, step out of the editing suite into the meta-editing suite, look at time represented as a film of a film, and count and cut up the film into 9 pieces, each one showing the act of identifying something happening. So what I'm saying here is basically that if we think of counting and addition as happening in time, multiplication involves time compounded on itself, or time times time, time squared. And this is the interesting bit. It's a kind of feedback. We're taking numbers and we're applying them to themselves. Rather than counting things, we're counting numbers themselves. So we're feeding the number back system back into itself, rather like if I hold a microphone up to a speaker, the system feeds back on itself, produces this unexpected output. And I'm suggesting that the distribution of prime numbers, the result of introducing multiplication into the number system, and all of the mathematical weirdness that goes with it, is a form of consciousness feeding back on itself. And hence this bizarre notion of there being some kind of dynamical, quantum mechanical, vibrational system underlying the number system is actually something, it's telling us something about consciousness. I don't know what, I don't understand this at all, I just find it very strange. But I'll end with a quote. This is from James Sylvester, a great 19th century mathematician and poet. He writes here in rather florid Victorian language, so I'll translate it once I've read it out. I've sometimes thought the profound mystery which envelops our conceptions relative to prime numbers depends upon the limitations of our faculties in regard to time, which, like space, may be in essence polydimensional, and that this and other such sorts of truths would become self-evident to a being whose mode of perception is according to superficially as opposed to our own limitations and linearly extended time. What does he mean? He means this: I have sometimes thought that if we were able to perceive time in some multi-dimensional way, more like a surface, he said superficially, he didn't mean shallow, he meant like a surface. So if we could perceive time in some surface-like or multi-dimensional way, then the distribution of prime numbers and related mysteries would not seem mysterious to us at all, it would seem self-evident. So some homework for any psychonauts in the audience. If you ever find yourself in a particular state where time appears to be multi-dimensional or surface-like, have a think about prime numbers and see if you come up with anything interesting and report back to me, secretsofcreation.com. Thank you.